Excited to have a distinguished panel and a distinguished group, and thank you all for being here in the final week here of session in Congress and of everything that's going on. So we know you're busy, so thanks for taking the time. I am Andrew Holland, the Senior Fellow for Energy and Climate at the American Security Project. We are a nonpartisan national security think tank that looks at a range of national security issues, everything from war and peace in the Middle East to nuclear nonproliferation to next generation energy. And that's what we're here today to talk about, is understanding what's next in fusion energy. And we have a distinguished panel who I'll introduce in a minute here. But I wanted to just take a minute to introduce you all, and I know we have a varying audience here, people who have decades of experience in the fusion community to people who may not know what fusion is. So we're going to quickly say fusion is it's basically the power of the stars. E equals mc squared. This is the Albert Einstein equation. A tremendous amount of energy inside of quite a small amount of mass. So as you can see on here, what is fusion? Heat and pressure. You're able to push together two atoms of hydrogen is the usual way of doing it. A fusion reaction in which helium and a neutron and a tremendous amount of energy is released. This is a nuclear reaction, but it's very different than the nuclear fission that we use for 20% of our electricity today. I'd encourage you all to go to our website and look further into this, but this was a project we did a couple of years ago to look at fusion's reach across America and see how fusion really touches 47 out of the 50 states, over 775 research institutions and businesses supporting fusion, at least 1,200 direct research positions in the fusion industry. And again, this was a couple of years ago, so it's likely gone up since then. All of that's to say that fusion isn't something that's perpetually 30 years away, as you may have heard. It's something that's happening right now in labs all across the country and all across the world. And we're pleased to have a great panel here of scientists working on fusion right now. And again, go to our website, but this is kind of our why the American Security Project cares about fusion. Clean source of power will revolutionize the energy system. It will address the climate crisis in a relevant time frame. I think that's important to talk about when we've got just finished up the COP21 without figuring out how to meet the ambitious goals that they've talked about. So it's important enough to get there. It will establish a high-tech industry. It will allow the creation of an exportable technology that will allow America to capture a portion, and this is important, the estimated $37 trillion in energy investment in the coming decades. That's energy investment that's going to happen in something, in some way, in some technologies. So what will that investment be in, and will it be in yesterday's technologies or will it be in 21st century technologies? So with that, I'm going to introduce our speakers here, and we're going to go from right to left today, and each of them will talk for a relatively short time period, 5 minutes, maybe a little bit longer, but we want to have a discussion with you all. The reason that we're here today is because there are new developments in fusion. There is new advances going on, new scientific advances, but also new business advances. We've got, it's new advances in materials science, new advances in engineering that allow the previous existing science to move forward. So going from on my left here, Dr. Dennis Whyte is the head of MIT's Nuclear Science and Engineering program, and they're director of the Plasma Science and Fusion Center. Michael Delage is the Vice President for Strategy and Corporate Development of General Fusion. Thanks for being here, based in Vancouver. Doug Witherspoon is the President and Chief Scientist of Hyper-V Technologies Corp. He's based here in Chantilly, so just a short drive in. And Rich Barth is the Senior Vice President for Government Relations and Communications of Tri-Alpha Energy. He's based here, but Tri-Alpha is out in California. So we're excited to have them all here. We'll hold your questions to the end, but we'll have plenty of time for all of that. So with that, I'm going to turn it over to Dennis here.
Thanks, Andrew. Thank you, Andrew. So I usually start this by giving my what I call my airplane seat sampling. That when I sit on an airplane, I consider the person sitting beside me as sort of this random sample of a person from the American public. And they see I'm working on some slides, because that's what we do on the airplane. And they say, so fusion, you still do that? That's cold. Is that cold fusion? Is that, is fusion real? So the first thing to get out of the way is fusion is absolutely real. It happens in laboratories all over the world almost every day. So fusion experiments actually create the conditions, which Andrew pointed out, which basically are recreating to a proxy the conditions at the interior of stars. With temperatures which reach 100 million degrees, we actually make fusion reactions happen, okay? So it is real. But what we're actually working on, in fact, that's what you're going to hear today, is about how to take it from there and look at some new ideas about how to get fusion energy, which is fusion science is real. Fusion energy is something that we're working on. So that was the beginning of this slide, is that the perception is dated, and in fact, I would argue that it's a very exciting time in fusion, because really almost when we need it most, and we're thinking about on what kind of timeline we can make fusion occur, that there's some new technology and science are putting fusion more within reach, we believe. So first of all, it was, and in fact it featured many of us up at the front of this, at the table. There was a Time article, and in some sense it said it best, and you can't probably read it from there. It says, unlimited energy for everyone forever. So just besides that little, we're ambitious if nothing else. So you'll hear about some other ideas. What we've been working on at MIT is actually is taking a look, and it's probably why we started with us. We're looking in some sense at the traditional confinement methods that have been used to recreate these conditions for fusion. It's a particular device called a tokamak, but it's also essentially called magnetic fusion energy. And what we've been looking at is actually the advent of some new technologies which have become available really in the last 5 years on the industrial scale. In fact, I'm holding it right here in my hand. They're called high temperature superconductors. These high temperature superconductors, for instance, this can carry 1,000 amperes of current, which is like 3 or 4 households worth of current, with no dissipation. It's sort of like amazing stuff. What we've realized, and through a study largely carried out by MIT students, that what we've looked at is basically a reimagining of some of the engineering choices that you would make moving forward with magnetic fusion. And this resulted in a conceptual design called the ARC fusion power plant. Then you can see the person, that's it right there, and you can see the person standing beside it. It's quite compact because of the ability of this new technology to make it very compact and basically make something like 250 megawatts of net electricity based on rather established science. Next slide, please. So it is really a breakthrough, because of the superconducting technology allows us in the laboratory, actually already demonstrated, in fact, at smaller scale, a doubling of the strength of the magnetic field. And you say, well, doubling the field doesn't seem like much, but it turns out when you work through the science of this, is that the amount of power you're allowed to make in a given set of physics rules scales like the magnetic field strength, which is this B value, this is the only equation, don't worry, to the 4th power. So if you double the magnetic field, that's 2 times 2 times 2 times 2, because you multiply it 4 times by itself. So it's a factor of 16 improvement. And that's a bit of a simplification, but that's essentially what we've used, is to actually use this established science to take a device which actually already in the United Kingdom has shown that you can make 10 million watts of fusion power, take that science and scale it with stronger magnetic fields to actually make hundreds of millions of watts of fusion power. And basically in a device which is the same size. So that's the motto that we have, is that if we can make the devices that make fusion work, then we can get fusion energy on a smaller scale, and that will make it occur faster, which is sort of almost self-evident to us. So finally, what we've also laid out in this is that there's a lot of interesting critical R&D that actually needs to occur. This is actually commercially available technology. What is not available yet is actually taking this and making, I won't go into the details of it, but basically making very reliable magnetic fields using this new technology. It's within reach. We've already demonstrated at small scales in the laboratory, but actually where this needs to go is we sort of see a timeline of like the next 5 years with a rather modest investment could actually get you to a demonstration at small size of this new magnet technology. We're considering something called SPARC, which is our little local acronym, but which means soon as possible ARC, because our ARC is we're very good at acronyms at MIT. What can I say? And ARC is the idea, is a sort of an end goal where we're talking about a fusion electricity pilot that would actually put electricity on the grid. It's more conceptual because we have to develop the technologies to that. And in the interim, we're imagining a fusion energy pilot, which is SPARC, which is at a smaller scale. And you can see the person standing beside that. So that's basically our take on this, is that we've done a lot of work to establish the science of fusion, and we believe that there's a new set of technologies, and I've only described some of them, which actually put this within reach, we hope actually sooner.
Dennis, thank you. New technologies, developing new areas in fusion. With that, I'll turn over to Mike Delage of General Fusion. Mike, thank you for being here.
Thanks a lot, Andrew. Is the mic on?
Yeah.
Okay. Bring it a little closer. Okay, so thanks very much. General Fusion, we're a company, as Andrew mentioned, based in Vancouver in Canada. We're a private company, which makes us similar to some of the others up here, but relatively unusual for the history of fusion. It's one of those things that's one of the exciting new things going on. So we're backed by investors across North America, some in Europe, and also in Asia. We're a company of about 65 people, so this is a serious endeavor. We do a lot of partnership with the fusion science program at universities and national labs in North America and elsewhere. So we're really building on the backs of what Dennis talked about, which has been several decades of some significant advances in fusion science. What's different about us now is, and you'll see this with some of the private companies, is we're taking a look at a little further down the road and saying, well, what is it going to take to get to an economically viable power plant? And rather than going down sort of the latest iteration of science, can we step back for a second, look at the technologies that are available today, whether they're new technologies or existing industrial technologies that would allow us to get to a fusion-based power plant that would be competitive economically with fossil fuels. And that leads you down some different paths sometimes. And in our case, we're pursuing an idea called magnetized target fusion, which is a bit of a hybrid of existing approaches to technology that have been researched in national labs. The large scale or the magnetic fusion systems, which are purely about confining plasma, and then on the other end of the spectrum, laser fusion research like at the National Ignition Facility in Livermore, California, which is a purely compression system. So General Fusion scheme, I don't know if the animation is running, Andrew, but it's a hybrid of these two. So we form a magnetized plasma, but relatively short-lived. So we try and avoid some of the long challenges of how to keep one of these plasmas hot and stable for many seconds of time. And then what we're going to do is compress it. But the compression speed can happen on shorter or on longer time scales than in purely laser fusion because we have that magnetic field. And that allows you to use technologies which are much more common to ones we're used to seeing industrially. So our compression technology is actually driven by pneumatic systems. Steam-driven pistons set up a pressure wave that compresses our plasma. Well, steam systems are ones which we know how to build industrially at large scale. The timing and synchronization of these is based on all of the advances that we have made in electronics over the intervening decades. And so we can take advantage of really the advances in electronics to make something like this happen. The technology for making the plasma that we need has come a long way in the decades since some of these ideas were first conceived, and so we can actually start to build these things at large scale today. It's okay, guys, just go to the next stage, the next slide. It's crashed completely. Gives me longer to talk. So what we're doing as a company is really trying to say, well, this is an idea that actually magnetized target fusion goes back a number of decades. And the technology today, thanks to advances in electronics, it really allows us to pursue it commercially on a budget that fits within sort of the tens of millions of dollars of range rather than the multi-billion-dollar large-scale projects. And we can prove out the key underlying science and engineering of this technology on that scale, which allows us to use private capital to go after it. And that allows you to move with more flexibility and speed in some ways. And the idea being that if we can demonstrate the fundamentals and we can demonstrate the key underlying pieces of this technology, and here you see what's called a plasma injector. This is the magnetic side of what we do, is making a short-lived plasma, but you can see it's a fairly large-scale machine. And then if you look at the next slide, this is a prototype of the compression system. I talked about big sort of compressed gas-driven pistons. This is these large pistons around a smaller scale sphere. So we're building these things. We're building them at significantly large enough scale to be able to prove out the underlying technology and the underlying science, with the goal that if we could demonstrate that these pieces fit together, then this opens up a path to fusion that is decades sooner than maybe the mainstream approaches, and on a path that, when you run the numbers on the economics, looks like it can be competitive with fossil fuels. So as Andrew says, we need an answer for fusion that can help us solve some of the climate challenges and the energy challenges and attract some of that investment. And we're really hopeful that this is one of the ways that we can get there.
Mike, thank you. General Fusion has been a great supporter for ASP, so thank you for being here. Next, I'm going to hand it over to Doug Witherspoon of Hyper-V. He's part of a consortium that's received a grant from ARPA-E, and he's going to explain more on that and what their technology is doing. Thanks, Doug.
Hyper-V is a small company. We're only 6 people at the moment, but we've been... There you go. But we've been collaborating with Los Alamos National Lab and Scott Shue for about the past 7 years, trying to develop plasma jets for something I'm going to tell you about in just a moment. As Andrew just said, we're funded out of the ARPA-E Alpha program, which stands for Accelerating Low-Cost Plasma Heating and Assembly. It has a number of program objectives, which are ideal for what we are trying to do. If you look at the plot on the left there, it's just a visual to give you some indication of where we occur in the parameter space. Magnetic fusion is on the left. Relatively high stored energy for devices like tokamaks, ITER, et cetera. Although those might come down with these new systems that Dennis was just talking about. ICF, laser fusion on the right, requires very high peak power lasers. We're kind of in a sweet spot right in the middle there, very similar to what General Fusion is doing, but a different technology approach, where we can use basically off-the-shelf pulse power technology for driving plasma jets. And I'm going to show you that in a moment. The objective of this program is to try to advance the science and technology of MIF, and therefore kind of complement MFV and ICF, explore a region that really hasn't been explored very much before. The program also is trying to develop a low-cost entry into fusion R&D, and to attract further private investment in companies like General Fusion and companies like us, we hope. Next slide. What we're basically trying to develop is something called plasma jet-driven magneto-inertial fusion, PJMIF. It uses a large array of plasma jets to form a spherically imploding plasma liner to compress the magnetized target fusion target. So instead of using the pistons like General Fusion was using, what we're doing is basically taking a large spherical vacuum chamber, maybe 6 meters in diameter. On the surface of that sphere, we're going to place hundreds of small plasma jets, all firing towards the center of the sphere. It could be 300 to 600 jets, depending on the final designs. Those jets, as you can see, fire towards the center, and at some radius, inside that chamber, those jets are all going to merge and form the surface of a ball, basically, or a thin shell of a ball. And that shell is going to implode towards the center where you've got a magnetized target. Now, the trick here, or one of the useful features of this system is that it's kind of a standoff driver. There's no parts that are destroyed in the process of doing this, fusion. So it avoids the repetitive hardware destruction that some concepts have. It's kind of a near-term system, which will allow us to develop the technology with a high shot rate and good diagnostic access, so we know what's going on scientifically. Longer term, we can envision this operating at about 1 hertz, so 1 shot per second, with fusion energy being absorbed from that. The implosion speed of this liner is about 50 kilometers per second or more, up to maybe 100 kilometers per second. These are speeds that we've already achieved in the lab. And the reason we're trying to get this very high implosion speed is to overcome the thermal losses that occur as you're trying to implode the target. The whole system is kind of compatible with a flowing liquid blanket, which would absorb the energy on the outside. Although the details of how we do that still remain to be determined. But if we can make that work, it would avoid the need for developing the advanced materials for a first wall for things like tokamaks, which would involve billions of dollars in many years. Let's see, next slide. The plasma liner experiment is our first project to try and implement this concept scientifically. What we're going to be doing at Los Alamos National Lab, where we have a vacuum chamber that's about 9 feet in diameter, we're going to be mounting 60 plasma guns on the surface of that vacuum chamber. The little boxes that you see on the outside of each one of those guns is the pulse power driver that drives that gun. And we'll be developing about 1 megamp of current going through each one of those guns and firing towards the center. The blue central area there is representative of the plasma jets as they come in and form that liner. We'll be doing a lot of diagnostic work on that system, the point of which is to basically do this first ever spherical implosion of a plasma in a configuration that would be useful for fusion. We'll be doing a lot of diagnostic work to try and determine or what the characteristics of that sphere of plasma looks like. It needs to be relatively uniform without lots of ripples or things like that, or the implosion doesn't work properly. And at the same time, we'll be trying to benchmark codes that will predict what will happen for larger systems and at higher energy. Our coaxial gun development work on this project basically is to take the systems that we had used in the past that were ablatively driven and inject dense, heavy gases like argon or xenon, which is what you want to use for these implosion plasma liners. We have to improve the engineering. We have to improve the precision of the mass and the size and the profile of this plasma as it comes in. So that's basically a snapshot of the plasma liner experiment that's being funded now by RPE. We're just under contract just a few months ago, so we're just getting started building guns and preparing the vacuum chamber for the experiments to come next year. Our first attempt will be with 9 guns. That will allow us to look at a subset of the liner, and then after that, we'll go to the full 60 guns. So I think I'll stop right there.
Doug, thank you. Very interesting and exciting program. Next up, I'll pass it over to Rich Barth. Those of you who have been around fusion for a while, we've talked about Tri-Alpha, but For a long time, we didn't actually talk to Tri-Alpha. So it's really wonderful to have Rich here and to have Tri-Alpha joining us here today and joining the whole discussion about the future of fusion. So, Rich, over to you.
Thank you, Andrew, and thank you all for coming out today. Tri-Alpha Energy has been around since 1998. It was founded by a number of high-tech lovers out in California, near the University of California, Irvine, which actually birthed the technology that we've been building upon for the last 17 years as a corporate entity. I've been with the company for about 5.5 years here in Washington, D.C., primarily representing them, briefing up folks at the Department of Energy, White House Office of Science and Technology Policy, State Department, of course, DOE, et cetera, to make sure that we were in a no-surprise mode when we did emerge from stealth as we did just this past fall. Last June, on that machine that's pictured up there in the slide, last June, we reached an experimental model of what we call long enough in very simple terms, maintaining, containing, and holding a plasma at a steady state position long enough that we can actually predict that if we had enough power to continually pump into it through those accelerator beams, which are the yellow cans you see ringing the center chamber, we could continue to pump enough power into it, we believe we could maintain the plasma at will. And so that goal was achieved. It was a significant scientific milestone for us as well as for our investors and our science advisory panel. And that is depicted in the slide that's up there now. That slide actually shows our long and tortuous path to achieve this at-will containment of the plasma. From a number of years ago in the early 2000s, we continued to build further and further a controlled plasma till we achieved that top red line. And the reason it runs out of steam shortly after that 5 milliseconds is that the accelerators that were on the previous slide were only built and designed to provide energy into the plasma for about 7 or 8 milliseconds. But we believe that the theory simulation work we've done on computers matches up extremely well with the very reproducible plasma control that we demonstrated back in June. That led to a Science magazine article in early September and an avalanche of further scientific exposure that we've had in the physics and plasma communities. Andrew had asked that we also anticipate a little bit what's coming up for the various enterprises that are up here addressing you today. We are, on March 15th, going to break down that machine that you saw. It's about 75 feet long, 35 feet around with its various componentry. We're going to break that machine down after some more than 45,000 experiments run on it and its immediate predecessor, and quite possibly could achieve 50,000 experiments, with each experiment having somewhere between 800 and 1,100 diagnostic analyses run for each experiment. So we have a huge data cube that we've learned on. And we're going to rebuild the machine using only some of the components you saw up there to be about 50% larger than that machine, which currently operates at about 11 million degrees C for the plasma. And the larger machine, again, about 50% larger in the current space we have, will take us about 12 to 14 months to build. And when we fire up that machine, the scientific objective will be to determine if we can confirm without question what we call a scaling law, which is that the hotter this particular plasma gets, and I'm not going to go into details and keep you here for the next 3 hours, the hotter our particular plasma gets, a field reverse configuration, the easier it is to contain. And that's really a very unusual condition for plasmas. We have demonstrated it in the smaller machine that's still operating. We expect to get to 30 million degrees in the next machine that we expect to build over the next 14 months, and hopefully within 2 to 3 years have confirmed that scaling law, which will lead us to then move in additional directions to produce fusion-based energy. And again, I will also stop it there so that we have a good amount of time for Q&A.
Rich, thank you, and thank you to all of our panelists here. we're excited to talk about this. Now, you'll see, I'm going to open it up for questions here. I've got a few I could ask, but I want to hear what you all have to say. Now, we do have some microphones there behind you, so you're going to have to stand up and go to the microphone so we can hear you on the video as well. So I'll ask you, when you do make an intervention, to state your name and affiliation. So thank you. Who's going to be first to go to the microphone? Go ahead.
Hi, good afternoon. I'm Stephen Dolly. I'm a reporter with Platts Nuclear Publications. Thank you very much for holding the briefing today. Had a little joke at the beginning about how fusion is not 30 years away, and of course that's been the running joke in the energy industry, at least since I've been covering it. But in none of the presentations today did we hear anything about what the commercial timeline is now. I understand there's still a lot of basic R&D to be done, and that's what you talked about in each of your projects, but can you give us any sense beyond in a time frame relevant to climate change, which suggests geological time frames to me, but can you give us any sense, for those of us coming at this from more of a business angle than a science angle, of how long it might be before any of these technologies could potentially be commercialized?
I'm sure none of you have had this question before. Anybody want to take it?
Well, maybe I'll first preface by saying that you get yourself into trouble pretty quickly when you start to promise dates around fusion, given the potential of the technology. And so we're all reticent to try and lay those kind of goals out there because there is basic technology development risk that needs to be overcome, and that leads to uncertainty. So I will say this, though, that we're private companies, and so our objective is to get there quickly. And the milestone for us isn't necessarily getting to the point where we're putting power on the grid, but I mean, obviously that's the long-term goal. The key for us is to get to the point where we can really get the rest of the energy industry engaged and excited about this technology. And I think that fusion needs to take its seat at the table alongside other renewable energy sources as part of this solution. And I think the proof points that we can get out in the coming years, and I think Tri-Alpha's demonstrated one of them this summer, gets us there. And so that's really the near-term goal. In terms of power on the grid, it's tough to speculate. We're certainly aiming to something in a kind of, if everything goes well, a decade sort of time scale, but a decade sort of time scale. Yeah, 10 years in that range. But again, that won't be us doing it on our own. That will be with the rest of the energy industry working with us.
So I can comment to this. So we've been thinking a lot about this as well too at MIT. So one of the advantages of our approach is that we've built many of those kinds of devices that I showed you up on the around the world, and so we sort of have an idea about how long it takes to build devices of different size, and this is why we think that we actually built, of the ones that we were showing that could be, for instance, an electricity pilot that would put in that electricity on the grid, we actually built over 25 years ago 3 devices that were of similar size to that, and we know that those took around 5 years to construct. This is one of the motivations for our approach, is that namely take less extrapolation in the science risk and put it into some new technology, basically putting the risk in technology instead, having a rapid plan to prototype that technology in 5 years, and then you could also be looking at decadal sort of timescales for putting electricity on the grid. So there's an approach which I think is shared by everyone up here, is that you need to come up with a pathway that says that in fact fusion energy doesn't happen too late. Right? Yeah. I mean, we have different ways of getting at it, but I think that that's actually very compelling to all of us up here. I'm speaking for the rest of them, but
just to follow up really quickly, it's hard for me to parse the 10-year time frame in the context of some of the discussions we just heard. It's going to take 12 to 14 months, I guess, just to rebuild someone's test bed, but we're going to potentially have power on the grid in 10 years?
Not for us. We're probably under realistic conditions, maybe 15 years to get to the point where you can do a demo. But putting power on the grid is another step after that. So that assumes a lot of good things happening along the way in terms of the research, and we don't run into any stumbling blocks.
Yeah, I just was going to.
And realistic funding.
That when I talk about power on the grid, I don't mean dozens of power plants. I mean, that's the first time that we look at it. And,
Yeah.
and the wild card here is we don't really know very well how transformative this could be and how much resources come available. So with what we have today, you could say, it takes 12 to 14 months to rebuild a machine or these sort of things. But when there's a tipping point that will come where this becomes clear that this is a technology that is moving out of the experimental development phase and into something where we're into commercialization. And I don't think any of us can really anticipate what that would mean in terms of how fast we could go and the resources that might be available. So these are goals, and they do depend on a broader community of support to get there, but we'll see what happens, right?
And you have to, so this is, it is confusing, I think, a little bit, is that there's a variety of different steps and goals that you can show. I mean, in my own view, if we could stand here and show you tens of millions of watts of fusion power being made continuously for some period of time, does that convince people that fusion energy is real? I think it does. It's not necessarily that you're at the place that you're putting economic net electricity on the grid. That's another step, in fact, of development. But again, we can't wait for too long on this, and that's actually why, in my opinion, we need a variety of approaches actually that attempt to do that, of showing significant progress and real fusion in decadal timescale.
Yeah. Questions?
Hi, excuse me. My name is Mary Fraker, and I have a political question that relates to time horizons. I'm wondering what ordinary citizens, including those of us who live in D.C. and have no voting representation, but actually ordinary citizens all over the country, what we can do to counteract what I guess I'll charitably call the considerable mischief that will probably be made by the fossil fuel industry.
Well, maybe I'll jump on that as I spend most of my time around D.C. in politics. And, I haven't seen any evidence thus far of any mischief by the fossil fuel industry. I've seen quite a good bit of collaboration with some of the energy industry out there on this, and maybe more interest is as the case may be. I don't think there's anything. I don't think there's anything more out there on this right now. Right? Sir.
Sorry, maybe I'll just point out, too, that one of our investors is a Canadian oil and gas company. And just to back up what Andrew said, that Cenovus Energy has been a very proud supporter of General Fusion for many years now and continues to invest.
So,
Sure.
I'm Oren Durrell from USA Today. I know that no one here is from Lockheed Martin, but I was wondering if they came out with a video or a statement at a TED Talk some time ago that got a lot of attention. I was wondering if any of you can either talk about what they're proposing, or whether any of your proposals or plans are similar to what they talked about, and also are there any risks to this technology, and if you could talk about the international ramifications of what you're doing, and whether there are other projects that are happening overseas that compete with or are also advancing the field.
So I should mention we did invite Lockheed Martin to participate. And maybe the request didn't get to the right people in the company or whatever, but we did invite them, but I'll leave that to them to answer on that. But competition and risks out there, anyone want to jump in on that?
Well, I could make a comment to the international stage. So, I mean, this is going on around the world, not just the United States, of different approaches to fusion. And in fact, there's the person sitting right beside you is actually part of a startup company in the United Kingdom, which is actually also taking a look at basically a different kind of configuration and new technologies to get to sooner, faster fusion. So. There are a variety of different. I would just say it is more than a United States effort, certainly. And of course there's a very large international experiment called ITER, ITER, which is being built in the south of France right now, which is a large, basically multi-government consortium to build that experiment.
Yeah, I would just make a comment with respect to the risks you asked about. The risks of meltdown are non-existent for the fusion science that we're involved in. And that's, of course, considered by the general public to be the largest single risk. And with respect to radiation, it depends on your approach to the fusion. One point of our efforts is to try to create what scientists call aneutronic fusion, which means that the fusion reaction that's predominant in our plasma ultimately will be made up of fusing hydrogen and boron, and they're both extremely benign substances. And the outcome of the product of the fusion is 3 helium atoms. Tri-alpha has named itself after its product, which we don't yet manufacture, but that's beside the point. Indeed, the risks are, we believe, extremely low. We've had some work done by a major university in North America here, and they have suggested that the risks of side reaction radiation are minimal along the lines of that which occurs in medical isotope facilities, which are generally located in suburban areas with very, very low risk profiles.
Hi, I'm David Kingham from Tokamak Energy in the UK. I'd like to follow up on the previous question. So at Tokamak Energy, we are working on compact spherical tokamaks using high temperature superconducting magnets. So we have a lot in common with MIT and Dennis's group's work on trying to get these tokamak devices smaller and to use this new material, high-temperature superconducting magnets, which we think are the essential key technology if tokamaks are going to get to produce commercial fusion power. Because enough is known about the basic device. If you could just get that field strength a bit higher, then you get into a very exciting region. There was another point about Lockheed Martin. Now, to me, the exciting thing about Lockheed Martin was they sketched out just how quickly a technology could be pushed into mass market, to global electricity scale, if they could get a good concept to start with. So it seems to me there's a really interesting sort of target there for many of us trying to start up new fusion activities. Can we get to the stage where Lockheed Martin or someone like them would think this has got to the point where we can invest, billions to scale up very dramatically? So Lockheed Martin's concept that they're working on themselves is a candidate for that, but there could be other candidates that would fit into essentially that rapid commercialization path. And you can see there are many manufacturers of things like jet engines who could indeed scale up a complex technology, deploy it very quickly, if someone makes the first one work.
It was a perfect comment, and I think we're quite right on that. Next question here, maybe sure.
Ryan Bucas, Gadfly. With respect to the question that was raised on timescale, I wonder if you'd comment on the relationship between investment and timescale, which is to say, if there was investment of roughly 1% of the U.S. defense budget, would that not, in fact, annually, would that not, in fact, bring online fusion energy within a decade?
U.S. defense, yeah, no, U.S. defense budget is $600 billion a year, so it's $6 billion.
Maybe instead of necessarily the U.S. defense budget, the global subsidies for fossil fuels is around $500 to $600 billion. And so,
keep it as a small number.
so if you were talking about 1% of that, I think you're talking about the same sort of scale of investment. And I think that's maybe one of the things that's exciting. I was in Paris last week for a few days at the climate summit. The discussion around the need not only to rapidly deploy the technologies we have, but also to make the investments in R&D into the technologies we're going to need in 10, 15, 20 years as we go from 10 or 20% reductions in emissions to try and look at how do we get to 50 to 80 to 100% reductions in emissions. And where are the resources going to come to develop and deploy those technologies? One of the big areas they're going to have to come from, which is where the capital in the energy industry is today, which is in fossil fuels. So we have to look to that industry and their choices around investment in R&D, I think, to accelerate some of the alternatives, including fusion.
So I mean, if it was at a level that was like that, then you can consider what you would do, like you do in any kind of strategy where you need. That basically means you're going after a problem on a very fast time scale because you need it very badly, and you're going at it. So what you do is you take probably all four of things that we're doing up here, and I'm throwing a few others as well too, and I can tell you what those are, and because you could go for it actually in that level, and you would actually then sort of have probably a couple of working concepts actually at the end of that in probably 10 years. Right, and that's actually that's a different approach than what we're doing right now. You can see that what we're all doing is sort of trying to look into the future to see about what is really going to be the key feature of fusion energy that's going to make it look attractive as an energy source. And we know, by the way, this is not a science argument that we're talking. None of us is debating about whether or not fusion is scientifically feasible. We're sort of talking about, which probably to you look like details about technical readiness and technical choices that you make. In the end, we know this can work. We're just, we're looking for a way to make it happen sooner. Yeah.
Yes. Hi, my name is Umair Irfan. I'm a reporter with Environment and Energy. Sort of a follow-up to that last question. Fission and fusion have both very different physics, but practically, in terms of finance, they run into the same problems, namely that the costs are front-loaded, payoff is years down the line. And so with that respect, how do you get around that? Is there a business model that you have that may be viable for fusion?
Business models. Go ahead.
They run business.
Yes, I think I don't think that we are necessarily locked into having to go to distributed energy sources. Also, although one of the commonalities you'll see with a lot of the fusion concepts is aiming for smaller scale, maybe than the sort of gigawatt to 2 gigawatt scale machines that people are talking about in the fission industry. But the other thing is a lot of the cost wrapped up in the fission industry is tied up because of the risks involved, and we already talked about the risks that don't exist in fusion. And so when your safety issues and therefore your regulatory concerns are lower, when you don't have the long-lived, and I'm talking the millennia-long waste streams coming, which you do in the case of fission, when you can avoid in the case of fusion, then there are opportunities to make these things much more cost-effective. And I think that's a key part of the story.
For the EJMIF approach,
Yep.
Oh, there we go. One of the key features of that approach is to, as Mike said, try to focus on smaller systems instead of the gigawatt or 2 gigawatt size power plants. Focus on the 100 megawatt or 200 megawatt kind of size. A lot of the technologies that are used in making such a power plant are, to a large extent, off-the-shelf type technologies. Pulse power technologies have been around for decades. We're going to push them a little bit further in certain areas, but they're not huge development efforts. So the cost of developing the systems to the point where you can get to a demo or break even or something like that is very modest compared to something like ITER, where you need a huge system. at very high cost. So that's one of our approaches for that is much lower cost and faster development time.
And so we've been looking at this too, in some sense, in the more standard approach of the tokamak, but looking at how can you make it smaller so that you remove this impediment of an initial such a large upfront single cost that it impedes even science experiments, let alone commercial products. And then the other part to emphasize is modularity. The idea of moving fusion systems away from single one-off devices. This is actually one of the impediments right now in fission energy, is because these are essentially one-of-a-kind devices that are built in different places. And in fact, in our department, on the fission side, we're working on ways to combat that. On the fusion side, I think a modular approach where as much as possible you have things which are built in centralized places then put together in the grid later on is absolutely key to an economic model which makes more sense for fusion energy. So all of those features should be looked at.
Ma'am.
Yeah, I think this is actually related to Dr. Whyte, to what you were just saying. I'm Carla Hagan. I'm a science fellow with AAAS working here in the Senate. And this is a question about moving from outside the lab into commercial scale. And so I think it's helpful for us on the Hill to be aware of what are some of the issues. I hope this is not too of a premature question, but I think it's helpful for folks on the Hill to be aware of what are the issues that you anticipate as you try to move out from the lab to commercialization. And so can you give us an idea, are there critical periodic table elements that are an issue, red tape with permitting on a nuclear, on a power plant, et cetera? What are the issues you anticipate?
Somebody else want to go?
Go ahead.
I'll take a quick shot at part of that at least. Nobody's ever built a fusion power plant yet, so very hard to anticipate some of those problems downstream. Once one or the other of us or some other venture in the UK actually gets to the point of building a power plant, then, unfortunately I've lived in Washington too long, then the problems will arise.
Do that.
I mean, so some of this we see already. I mean, one of the things I've been doing is this, in some sense inspired by what these guys at the table have done, is have a discussion outside of the standard sort of academic, government-only sponsored model. I see that what we actually are looking at is it's not possible that we can imagine a purely private industry actually going forward, because in the end this is a nuclear technology. So, but even with the vast improvements in safety and so forth that we're talking about, we're going to have to engage the government in some aspect of regulation in this. So. What I don't know what it looks like is what does a triad of sort of, I would say, basic research, academic research, if you want to call it that, industry and government look like that actually propels fusion forward? It's a really good question. Maybe you thought about it more.
Well, no, I just think the point you raised is really important, that these are not conventional companies in the startup sense at all. They're companies that work much more at a level of science than a lot of are normally doing. Then there are companies that work hand in hand often with the academic and national lab infrastructure. And that ecosystem is really important as we go forward, and the ability to partner with that ecosystem. That's one of the things that we've been talking about a lot, and I think there is some momentum around trying to find ways that allows, say, national lab scientists to take sabbaticals or to work seconded to private companies that are researching in the field for a period of time in such a way that they're guaranteed they can still go back to the national lab system afterwards without sort of risking their career. So there are little things that can be done that will help advance this field right away. I mean, there's obviously a big question about funding, which came up, and we can talk about that too. But there are things as well about how that collaboration between government and academia and private sector works, which can be enhanced, which could help a lot.
Yeah, in fact, one of the biggest issues, I mean, we're starting to think about this for our own case, trying to find private investment for the future. and that is that the fusion development process is not amenable to the usual venture capital model, which wants a product, and a payoff in 5 to 7 years. Fusion is definitely longer than that. And so there have been only a small number of success stories so far in attracting private venture capital, but so that's a significant problem for all companies trying to develop fusion.
Ma'am.
Marcia Freeman with Executive Intelligence Review. I wanted to get back for a minute to the international scene because even though a couple of things were mentioned in the UK, it's really been a couple of the Asian countries that have pushed very aggressively forward in fusion. And, Dr. Whyte's mention of MIT looking at superconducting magnets. There are 2 superconducting tokamaks that are doing experiments, and they are in China and South Korea. Both of those countries also, and Japan, have design teams now looking at the next step past ITER, right, the demo. And they're not going to wait 20 years until everything with ITER is finished to start the next machine, which we used to do in the 1970s. So it seems to me that this is wonderful political leverage, and I'm wondering, because even for the private companies, it's certainly wonderful leverage with the Congress in terms of, the level of funding for fusion that they're debating versus what's being spent in other countries, but also in the private sector, because when fusion does become commercial, frankly, these are going to be our competitors. So on the one hand, I would hope that there's international collaboration, like with MIT and these other tokamaks that are already operating, but also in the commercial field to use this, as a wedge, to be able to have people be aware of what's going on internationally. Have you come up against doing that?
Well, I would say I'd refer you all to our website, AmericanSecurityProject.org, and we have a report we did a couple of years ago on the international competitiveness on fusion, and there is a great deal of competition. But I also should say that I've been very impressed by the international collaboration I've seen in the area as well. When I've worked with renewable energy companies or something, there's none of this information sharing that you see in the fusion field. It's unbelievable. Any thoughts on working with or competing against?
It is competitive, but it sounds not like an oxymoron. It's competitive but collaborative. And in a way, it's because I think those of us who work in fusion actually see this is a global problem. This is not just a U.S. problem. It's not just a China problem. We're really doing this now. At the same time, we want to win, and that's the competitive part of it. So our own scientists at MIT collaborate very closely, in fact, with the experiments in China that were just mentioned in the last one. But we should be aware that this is another aspect of very serious people looking at are making big investments, in fact, in fusion, and we should be looking at that because that's an indication about how this is viewed as a possible energy source around the world. Yeah.
In terms of the competition, I think we would all tend to agree that we are competitors, but at the same time, we hope that the other guy also wins. Because it's not that the first guy is necessarily going to take all the fusion reactors down the road, but somebody winning in making fusion work helps all of us in the community. And so that's one of the reasons I think that everybody is more of a collaborative, sharing nature for the most part. So,
Yeah, we see a lot of collaboration. Our investor pool is quite internationalized. Our research partners reach around the globe, Asia, Europe, Russia, and so we don't view it as a U.S.-centric IP development kind of thing. It's a truly collaborative international effort. And I would add one factoid is that individuals who are working in our 140-person lab come originally from over 27 different countries. So it's truly an internationalized set of projects.
Wow. I don't know which one was first. So.
Go ahead.
So Samuel Brinton, recently of MIT, and now here in DC doing the Bipartisan Policy Center. This year I wrote a report which featured all of your companies, citing the over 50 advanced nuclear companies here in the United States that were developing advanced nuclear reactor technologies. And a lot of people were very surprised that I kept fusion in the advanced nuclear space, trying to make it not fission versus fusion, but instead making it a collaborative communication space. One of the major challenges that came up was that people said, well, we have very specific regulatory challenges for advanced fission, and then when congressional offices have me come in and ask me questions here on the Hill, they have no idea what the regulatory structure is for fusion, and I can almost give them no concrete evidence of what that regulatory structure is. So as each of your companies are being developed, and as academia is working on this project, who is taking the lead on trying to develop relationships and conversations with the Nuclear Regulatory Commission to try to develop a streamlined regulatory process, so that way when you get these companies ready, it's not another 10 years of regulatory development?
Anybody?
Big gun. Sorry, guys. I know it's a tough question, but it's one that I get all the time here on the Hill, and I'd really like an answer.
Yeah, well, so maybe we don't do a whole lot of engagement. We're based in Canada, and the regulatory framework there is different and does allow for us to move forward with clarity. In the United States, the Nuclear Regulatory Commission has suggested that they have jurisdiction over fusion, but that they are not ready to invest the time and effort in developing the regulations around that yet. So I don't know if others have had more engagement.
So one of the comments to this is that actually we're going through this experience with ITER in France. So there will point out is that in fact the nuclear regulatory body of the French government in fact has oversight over this. I'll point out some, it has very attractive features. For example, they've indicated, they don't need a site boundary evacuation plan, all very good. And then the other part of it is the reason why in the United States the engagement with NRC is not so direct. It's because most of the experiments have actually happened in Department of Energy laboratories, and so that's actually has a different framework. But now I'd say is that we have done experiments that have had serious, that you've been looking at nuclear safety issues, and we have it in all labs right now, and we have an exemplary record in this area. But that large-scale engagement with NRC has not happened really in the United States yet. Yeah.
Put it on the to-do list.
Thank you.
Sir.
Yeah, my name is Steve Peterson. I'm with the smallest of struggling startups in the alternative energy field, a little company called Deuterium Energetics. And was wondering, in the outline of the American Apollo program for fusion energy, it talks about alternate approaches. What alternate approaches is American Scientific considering, besides obviously plasma confinement?
Yeah, what alternate approaches? I think you're looking at them and all of them. We wrote that report, and again, go to our website, americansecurityproject.org, and you can download the whole report. We presented a 10-year plan for the development of fusion energy at the American Security Project. What's nice to say is that it's 2 years old and it is outdated. Things have advanced, things have changed in the last 2 years, and I'd say that the things that we're talking about today mean that a lot of the time frames and a lot of the money that we talked about in that report have changed. What specific alternative approaches were we talking about? Mostly it was talking about things like we talked about on this stage, but I think what we said in there and what I tell people on the Hill and elsewhere is that it's far too early to shut down alternative paths of that could go down. We need let a thousand flower bloom. Let everybody compete for the the research funding that's out there, and also, grow the pot of research funding.
You could also go to the RPE website and look under the Alpha program. There were 9 winners in that program with some really interesting stuff. So that'd be a good place to start.
Sure.
Just have a quick question. Creighton Jones. Just wondering what your guys' perspective is on the next generation of scientists to come into the fusion energy space. I know, for example, there was this group, the Ares group, which was sort of a cross-collaborative group of many universities, institutions. But as far as I understand, it had to shut down due to lack of funding, and UC San Diego basically shut down a large component of their fusion operations. So in terms of the next generation, do you see enough movement of people into fields that will contribute to fusion? Is that a real concern in terms of attracting the next generation of scientists to take up this work?
Since I come from the educational institution, of course it's a concern. In these areas, I can point to several of these critical technology areas where we have a single student in the entire U.S. program working on these. And that we actually relied on students in some sense to do conceptual designs of things moving forward, which is like an Ares-like activity that you pointed to. I mean, the good news I can tell you is that there's a generation of young people who are ready to roll up their sleeves and dive into this, because I see them every day, actually at MIT, and we just heard from one of our graduates. We better make sure, though, that we're putting together the framework that allows them to succeed, and that's what I'm worried about, is that if they, we need to catch this excitement and actually grow the number of people who are coming into the field, very capable people, and train them. So.
Adam.
Hi, my name is Adam Rosenberg. I'm with the House Science Committee, and full disclosure, I'm actually a fusion scientist by training. So I actually have a kind of technical question, now that all the policy stuff has been worked out, for Dr. Witherspoon. You're the one person on the panel I've never actually met with before, and I'm trying to understand your configuration a little more completely. So do you ramp up a magnetic field after you fire the plasma jets?
You mean for the target or in the plasma guns themselves?
So, after you fire the plasma guns, I'm trying to understand how you get to, do you form a spheromac or a field reverse configuration?
That has not been solved yet.
Okay.
There are a number of different configurations that are being looked at, including FRC configurations and compact tori configurations, things like that you would fire into the center of the sphere just prior to firing the guns, so that the lifetime is long enough for the implosion process. Other processes that could be used conceptually is to fire in a pre-compressed plasma kind of sphere that you then magnetize remotely using laser beat waves. That's been looked at. Theoretically, it's possible. There's been a little bit of experimental work. That's one of the things that we'll be looking at. Well, not us, but part of the program we'll be looking at in the future is ways of remotely magnetizing the target. So that's an issue for development for the whole concept is how are you going to make that magnetized target? It's not trivial, so by any means.
All right.
So,
all right. Thank you.
Thanks, Adam. Well, I think we've answered all your questions, and we've figured everything out, and we've got it all set up, right? With that, thank you all for coming, and thanks for your time today. And join me in thanking all of our panelists. Thank you.